In this problem, we are asked to maximize the function w equals xy plus 2yz, subject to the constraint x squared plus y plus z equals 3. So since we're maximizing a multivariable function subject to a constraint, we're going to use the technique of Lagrange multipliers. So that means we've got to note that we've got one function which we're maximizing, which is w. We've got another function which is our constraint, and we're just going to call that g. So the first thing we need to do is take the gradient of w, and the gradient of w, partial x is just y, partial y is x plus 2z, and partial z is 2y. Next, we're going to take the gradient of g, and the gradient of g, partial x is 2x, partial y is 1, and partial z is just 1. Next, we set up our vector equation, which says that the gradient of w must be a constant times the gradient of g. And of course, I prefer using c for the constants. Okay, so that's going to give us three equations. So the first equation, we get y equals c times 2x. Second equation will be x plus 2z equals c times 1. And the third equation, 2y equals c times 1. Okay. Well, from the last equation, we immediately know what c is, and we can substitute that into the other two equations. So in the second equation, we're going to get x plus 2z equals c, which is just 2y. And then in the first equation, we're going to get y equals c, which is just 2y, times 2x. So in other words, we get y equals 4xy. And that gives us that 0 equals 4xy minus y. We keep solving, and we get 0 equals y times 4x minus 1. So solving that out, that gives us y equals 0, or x will equal 1/4. So now we look at both of those cases. So in the first case, if y equals 0, what does that tell us? That tells us that from the second equation, x plus 2z must be 2y, so that must be 0. And that gives us that x equals negative 2z. So now we have a value for y at 0. We can replace x with negative 2z, and now we go back to the constraint equation. So going back to the constraint equation gives us x squared, so negative 2z squared, plus y, which is 0, plus z has to equal 3. So from that we get 4z squared plus z minus 3 equals 0. So next we're going to factor that. So a little bit of clever work gives us that 4z minus 3 times z plus 1 equals 0. And this gives us z equals 3/4, or z equals negative 1. So that gives us two different solutions. Next, we solve out the case. So we've solved out the case where y equals 0. Next, we solve out the case where x equals 1/4. Let's look at the case where x equals 1/4. And what does that tell us? So plugging that in again to the second equation, we get 1/4 plus 2z equals 2y. So we could solve this out either for y or for z. I'm choosing to solve for y. You get y equals z plus 1/8. And once again, we plug that into the constraint equation. And doing that gives us 1/4 squared plus z plus 1/8 plus z equals 3. Solving that out, and I chose to use decimal approximation, we get z equals 1.41. And then we have to figure out what y is because we don't know it yet. Y was z plus 1/8, so for y, we get 1.53. So that gives us 2 critical points from the first case and 1 critical point right here. So let's jot them all down. So what are our critical points? 2, 0, -1, and then negative 1.5, 0, 3/4. Those are both from the first case, and then from the second case we get 1/4, 1.53, 1.41. I've mixed together fractions and decimals. Forgive me that. Okay. So these are critical points. Now we want to find out which ones are maxes and which ones are mins. In order to find the maximal value for W. So we go back to the original function of W and we plug in the critical point. Plugging in 2, 0, -1 gives 0. Plugging in -1.5, 0, 3/4 gives 0. And plugging in the last critical point gives 4.69. So this is your max. So the maximum value is 4.69. And there's your solution.